We shall start. I just make also a cloud recording. Okay. Good. So we started, well, we already discussed something about deformations of holomorphic bundles. I mean, vector bundles, of course. But let me just remind you that analogous problem in topology is trivial. What I mean, that if we consider topological vector bundles or smooth vector bundles, so just a second. Like this. So for topological, let me call it recall. Topological or smooth vector bundles cannot be continuously deformed. It means that when we try to deform them, they remain the same. Excuse me, just a second. Like this. In other words, if we take as a continuous family of such bundles, which simply means that we take for a continuous family of vector bundles over X, some manifold, say, which means that we have a parameter space. Let us denote it by S, and we have a bundle E over the product X cross S. We regard X as a manifold where the bundles live and S as parameters. Then if we take two points in the parameter space, and consider a restriction of this bundle to the slices, to two copies of X corresponding to two different T1, T2. So E restricted to X cross point T1, and consider E restricted to X cross T2, then these two bundles are always isomorphic. This means that we cannot deform. Okay, now let me also remind you of a warning which was issued at the end of the last lecture. we learned that the space of infinitesimal deformations of a holomorphic vector bundle is given by the cohomology group, which I will write down now. So given a holomorphic vector bundle E, now X is a complex manifold as always on X. So the space of infinitesimal deformations will, as we learned, is given by H1 over X with coefficients in the endomorphism bundle of E. But unfortunately, in general, this does not coincide with the tangent space to the moduli space, even when some notion of the moduli space exists, nevertheless. Tangent, here I write tangent space to the moduli space if it exists at the point corresponding to E. The matter of fact is that the infinitesimal deformations are solutions to the linearization of the problem. So H1 with coefficients in endomorphisms. This is how we obtained them. Is only a space of solutions of the linearized problem. And what is the nonlinear problem? The nonlinear problem is the holomorphic structure on a vector bundle, which can be represented in terms of d-bar connection. So the nonlinear problem is to find solutions to the equation nabla bar squared equals to 0, modulo gauge transformations, of course. But if in local trivialization, or if the bundle is topologically trivial, in global trivialization, if we write the connection nabla bar, d-bar connection, as d-bar plus a-bar, then the zero curvature condition is like this. So it is clearly nonlinear. When we linearize, we come to the problem corresponding to finding elements of this cohomology group, as we discussed last time. So if we consider arbitrary holomorphic, say, or continuous also, family of holomorphic bundles, let me denote this family as a bundle E hat over X cross S for some parameter space S. Then the only thing we have a map from the tangent space to S at some point T to the space of infinitesimal deformations, that is H1. Where E is a bundle corresponding to the value T. In other words, E is E hat restricted to X cross T. But this map may not be an isomorphism. One can say that not an arbitrary first order infinitesimal deformation can be continued to a finite deformation. However, for the line bundles, the situation is good, and we always have the dimension of infinitesimal deformations is the same as of finite ones. So for line bundles, let me write it. In short, it's always okay. What does it mean? That if we denote by M the moduli space of line bundles on some manifold X, which is the same as Picard group of X, then the tangent space to M at some point T, at any point T actually, T in M, is always H1 of X with values in the trivial bundle O. This is because the endomorphism bundle of a line bundle is always O at the trivial bundle. Is it clear why? Not clear? It's because it's written this isomorphism, because the endomorphism bundle of any vector bundle is L star tensor L, which for line bundles is canonically trivial bundle. Let us consider an example for complex curves. That is, the dimension of X is 1. Then, and compact curves. Then the Picard, sorry?
Можно спросить?
Yes.
То есть как бы с линейным случае все хорошо, как раз потому, что там нет вот ни коммутативности, да, то есть там уже уравнение до плюса квадрат.
Because the initial problem is linear. This term is absent for linear bundles, right?
Да, а вот это вот отображение, которое в общем случае не изоморфизм, оно в общем случае инъекция, да? Которая
I'm not sure, and I don't know. I would expect the same, but strictly speaking, I don't know. Actually, to find out the answer, we have to describe this map more explicitly. But this would take time. I don't know, sorry. but it's to specific question. It should be answered exactly, but and therefore I'm afraid to say yes or no. But morally, yes, but in practice, I don't know. Okay. Now, the Picard group consists of components. So the Picard group of a curve is a direct sum. It is a abelian group, therefore I use a additive notation. It is a direct sum of connected components labeled by an integer number t, which is the degree of a line bundle. So it's the sum of integers. And each component, the two components are isomorphic as manifolds. They are not subgroups, therefore we cannot compare them as groups. But as manifolds, they are isomorphic. Try to figure this out. And each of them is the same as a Jacobian, as complex manifold. So this holds as for complex manifolds. Okay. Now, as you know, the Jacobian is defined as a torus, which is a affine space modular a lattice. As an affine space or vector space, we should take H01 of the curve, Dalbocka homology of degree 0,1, and take the quotient with respect to the lattice, which is isomorphic to the integral homology of degree 1. Now I have to show that this lattice is indeed something inside H01. This comes in two steps. First, the integral cohomology is a sublattice in real cohomology, in cohomology with real coefficients. But now let me consider it as a subspace in cohomology with complex coefficients. Sublattice. It's not a full sublattice, but nevertheless. It's subgroup, right? And the latter guy is split to direct sum of H10 of X plus H01 of X. And finally, we can project to the second factor. And this defines the needed embedding of integral cohomology into H01. And therefore, we can take the quotient and obtain the Jacobian.
Вопрос, я
Yes.
честно не помню, а ваш один от X до Z там кручения нету, да?
In the case of complex curves, there is no torsion. Yes. Therefore, it is this thing is really an embedding. But otherwise, we would take H1 integral cohomology modular torsion. But in reality, there is no torsion. Now, the tangent space to the Jacobian manifold, to the torus, at any point t, is of course the same as the space, the affine space which we used to obtain the torus. But I write it. Yeah.
Sorry, but you say that this is an embedding. This means that there is no kernel in projection. Yes.
In here.
Yeah.
Yes. Yes. That's right.
Is it obvious that there is no kernel in this projection?
Yes, it is, because look, the integral cohomology is embedded into the real part of complex cohomology group.
Okay.
So it's like diagonal here.
Okay.
Therefore, it projects in a one-to-one way. Yeah. Correct question. Okay. Now we see that the tangent space is like this, and the letter group is the same, almost by definition, as the first cohomology group of X with coefficient in O. So we confirmed what we knew from the general consideration. So in this example, we have exactly such property. Now, let us organize such a exercise. So the task is to prove the above statement, namely, the definition of Jacobian does not need a proof, but what does is that Jacobian gives us the Picard group. So this isomorphism has to be proved. I suggest the following steps for solving this task. So say A is consider peak null, peak zero. This is the moduli space of holomorphic line bundles of degree 0. That is topologically trivial bundles. The degree is the same as the first Chern class. Since they are topologically trivial, it is easily it's not hard to deal with D-bar connections in such bundles. So in a global trivialization, Any d-bar connection is described as an operator of the shape of such a shape where a bar is a global 0-1 form. Since we're dealing with line bundles, it's just a scalar 0-1 form, which the endomorphism bundle is trivial. Now we have to describe all 0-1 forms modular gauge transformations. So our problem is consider the space of such a bar modular gauge transformations. Of course, I mean d-bar gauge transformations. The condition of zero curvature is trivial. Because of complex dimension equal to 1. Okay, now recall this property, this Hodge decomposition, this one. What does it mean? It means that I can always represent a cohomology class from here as a one form, which is closed, has only anti-holomorphic component, modular exact ones. This sounds as nothing, but in practice it's very important. Now consider how to say let me write, due to Hodge decomposition, the first Dalbo cohomology group, which is the space of 0-1 forms. Oh, let me better write in this way. 0-1 forms modular exact ones, d-bar exact, is the same as d-closed 0-1 forms modular d-exact ones. Now, if we consider the right-hand side, we know that we can always choose a representative from the equivalence, from the cohomology class to be a constant one form in the sense of standard flat coordinates on the torus. So in more rigoristic terms, this would be harmonic one forms. But hoping that we understand each other, I write simply constant 0, 1 forms. That's it.
But we talk not only about torus, yes?
If we say in terms of harmonic forms, not only about torus, of course, but on torus, the harmonic forms for the flat metric are constant ones.
So these are constant in flat metric, yes? Constant forms.
But otherwise, you may not necessarily appeal to Hodge theory relating this to harmonic forms. You simply can say the following. The cohomology group in the right-hand side here, D closed modulo D exact, each equivalence class, each cohomology class is characterized by integrals of one forms over curves. All right? I don't hear yes or no. Again, given a one form from, let me take some other color. So it's just recollection from cohomology theory. So if we take some element alpha from here, its cohomology class in H1 is defined, is completely defined by contour integrals of alpha over all gammas. Okay? And on the torus, wait. Sorry. At some moment I should have said that, sorry, it was a mistake. Prove this for the curves of genus 1, which are tori. For curves of genus 1. Therefore, I was speaking about constant forms and on the torus.
And the statement that the A bar is a global 0-1 form, it's independent on.
For peak 0, of course. Peak 0 is always modular space of topologically trivial bundles, and therefore we have global trivialization, therefore connection is a global form.
Mm-hmm. But for...
But how to describe them, it's another issue. Here, it is quite explicit for genus 1. So now, for any such data, this data, one can always find a constant form which gives the same integrals. One can always find a harmonic, a constant one form with the same integrals, with the same periods. The conclusion is that any cohomology class contains a constant one form, and the only one, because if you change this constant, the some integral would change. One form. Okay, this is good, but not yet the solution of our problem, because in our problem we have to quotient with respect to gauge transformations, which is not the same as taking quotient with respect to d bar exact. So the next step, the space H01 of X, which is the same as we now know, the space of constant 0, 1 forms. Let me write in the following. In the space, there are still some points which are related by gauge transformations. Gauge equivalent points. That is, there are still some points A bar prime and A bar related by this relation. And since we are dealing with constant forms, it is the same as this relation, because G has to be anti-holomorphic in this case. So the problem is now to characterize the remaining, the remnant, so to say, of gauge equivalence, the forms of the shape G minus first DG, which are constant. Now, the following digression. Exercise inside an exercise, okay? And this exercise. Prove the following properties, or find out better, prove the following, that there is a one-to-one correspondence between closed one forms on any manifold, on any manifold, not only complex curves. Closed one forms with integral periods some manifold, say X integral periods and maps from X to the circle. And the relation is exactly as above. Say some one form equals G minus first dg, where G is this map. So the second, there is a high dimensional analog of this, at least one very important analog is when we consider two forms. So closed two forms with integral periods. We don't need this now, but just in the context of the item 1, it would be natural to mention integral periods are in one-to-one correspond. Here it is a little bit more difficult. No, let me formulate in different ways. There is for any close to form with integral periods, I can construct a topological line bundle with connection just a second. In the item 1, I didn't mention whether these one forms are real valued or complex valued. For real valued, as I said, the counterpart is a map from X to S1. And for complex valued, I have to replace S1 with C star. I write it. So here I write R or C. I mean, forms then taking values in real or complex numbers. And here it will be, it is more natural, by the way, would be to write here I, R, the imaginary axis. But I won't do this, okay? And then the correspondences with maps either to S1 or to C without 0. Okay. Here's the same. If a two form is real with integral periods, real valued, then the connection in the correspondence here would be unitary. If the two form is complex valued, then the connection is arbitrary. So I don't write anything here. Anybody who would understand this exercise would understand also these two possibilities, real or complex. Okay, a topological line bundle with connection nabla such that its curvature, two forms, say omega, such that the curvature equals to omega. And the question is, first of all, to understand this relation, and second, this correspondence is not one-to-one. No, we can take modular gauge transformations, which are smooth automorphisms, smooth gauge transformations. This is not one-to-one in general. And the additional question is understand the ambiguity. Ambiguity. I hope I spelled it correctly. Okay, now returning to our main exercise. What was this small exercise about? It was about that the one forms which can be represented in such a form with G, a single valued map to C star, are nothing but the complex one forms with integral periods. So returning to this, we obtain that peak 0 of X for genus 1 is H01 of X modulo the integral for the forms with integral periods. Okay. Good. So we this was everything here was an example how to understand the Picard group or the modular space of line bundles on complex curves. Okay, good. Now let us consider the situation with genus 0. So another example, I do not number examples, sorry. X equal to CP1. All line bundles are exhausted by the list of K, all right? Any line bundle is isomorphic to some of K for some integer number K. But here we have also a complete description of vector bundles, which is formulated as Birkhoff-Grothendieck theorem. It sounds very simple. Any rank k holomorphic vector bundle over CP1 is isomorphic to a direct sum of line bundles, and all line bundles like this is isomorphic to the sum runs from I to k, from 1 to k, because of rank equals to k. But as always, I'm not so. Just a second. Let me write here L. The sum runs O of Li. And I remind you that then E equals to, then the first Chern class of E equals the sum of these Li's. Good. By the way, the proof is quite beautiful, and you can read it in lectures by Hitchin, which I quoted in the beginning. All right, let us look at the deformations of bundles, of holomorphic bundles over the space CP1. In the case of line bundles, what are deformations? For a line bundle, which is sum O of L, the endomorphism space is, as always, is a trivial bundle. And the infinitesimal deformations are therefore trivial. X is CP1 here. And this is trivial because CP1 is simply connected. So there are no deformations. And this agrees with the fact that any line bundle is isomorphic to, for some L, isomorphic to O of L. There are no continuous parameters. No deformations. Oh, why I wrote in Russian? Sorry. No deformations. We have to make a break, I guess. And the Picard group, what is the Picard group in this case? Who can answer?
Picard group, just a point.
Oi. It's not oi.
It should be just a point, right?
No.
No, Picard group is case of CP1.
If it would be a point, all the line bundles would be isomorphic to each other.
Oh, so the whole Picard group, not just the connected component of the identity.
Yes, the whole.
Yes, yes, the whole should be. What is it? It's like a Z. Yeah.
Right. Okay. Now let us look at some bundle E, some higher rank bundle, which is always such a sum. Okay. The endomorphism space will be as follows. We have to take E star tensor E, and O of L star is O of minus L, okay? And what we obtain direct sum over I and J O of Li minus Lj. As this guy is also a vector bundle. And here we find out its decomposition into line bundles. Yeah, and the decomposition is unique up to permutations of terms. Isomorphic, unique up to permutations. Okay. Now recall that we are interested in H1 of this bundle. And recall that H1 on CP1 for O of L is 0 for L greater or equal to -1, and non-zero, or I better write it as it is isomorphic to C to some power weight. Let me see. Sorry, just it will be minus L minus 2 then plus oh no, L plus 3, is it correct? Vanya, rescue me. Is Vanya present? No.
Yes.
Correct. Yes, correct. For L. Did you understand what I did when I wrote first minus L minus 2? What was that? It was just, you should remember this actually. It's due to SER duality. So H1 on any manifold with coefficient, say, in line bundle L, no, for dimensions, for X of dimension 1, it is dual to H0 of X dual of L tensor with canonical bundle KX. For X equal to CP1, the canonical bundle is O of minus 2. So we get I write the same. L star is the same as L to the minus first. Now, if L was O of small l, then we get so these are dual spaces. In particular, their dimension is the same. And now, what is the dimension in the right-hand side? Now, it's another thing we should remember, that the dimension of H0 on CP1 of some line bundle O of D is D plus 1 if D is greater or equal to minus 1, and 0 otherwise. Okay?
And so shouldn't it be then minus L minus 1 instead of L plus 3 in the, well, the formula we have?
Let us check. So
Well,
when we pass to this line, or to this line better, okay? It would, here we have minus L minus 2 plus 1. Yes, you're right. Yeah, right. So minus, yeah. L was negative, okay, yes, right. It would be minus L minus 1. Yes. Thank you. Very good. Okay, this was, again, exercise for me. So what we see now? Something. Sorry, something is with my. Oh, I don't understand. Oh, now it moves. Okay, what was the point here? Yeah, now we see that if you look at our endomorphism bundle, that each one of the endomorphism doesn't have to be 0, because in such a decomposition we may easily find some numbers, some degrees, these differences, which are less than minus 1. Okay. So, for example, for E equal to, say, O plus O of 2, the endomorphism of E would be O plus O plus O of 2 plus O of minus 2. And each one would be non-zero. However, there are no continuous parameters, because by Birkhoff-Grothendieck theorem, we see that any bundle is described by only by discrete parameters. By Birkhoff-Grothendieck theorem, there are no continuous parameters. And this is an example when that not any infinitesimal deformation can be extended to a finite one. So I don't write the words here. This was the example. Okay. Now I guess we finish this the subsection about deformations, but let us make a break, 10 minutes break, and then we continue at 15:50. Okay, see you. Okay, let us continue. And just 1 minute more. All right. So now let us also recall one of the main source of information about cohomology of holomorphic bundles over curves is which is the theorem Riemann-Roch theorem. So for a complex curve, complex curve, and for a holomorphic vector bundle, a holomorphic vector bundle on it, then we have the following relation, and I denote dimension of cohomology group HP by HP. Then we have the following: H naught on X E minus H1 X E equals degree of bundle plus rank of E times 1 minus G. Together with third duality, this sometimes gives a complete description of cohomology. And other important things are the following: if say some proposition not related directly with Riemann-Roch, but which is always which is very often used, if the degree of a bundle is less than 0, then there are no holomorphic sections. Okay, now let us start subsection 1.8, which will be direct images of holomorphic bundles. First, recall that there is an operation of inverse image. So when we have two complex manifolds, say X and Y, and a holomorphic map, morphic map of complex manifolds, and E is a holomorphic bundle over Y, then we have its inverse image on X, and such that, for example, the numerical topological characteristics of this bundle are related also by the pullback, such that its rank, first of all, is the same as rank of E. The Chern classes of the pullback are pullback of Chern classes. And also, if we take any point in the source space, then the fiber of this point is canonically, by construction, is isomorphic to the fiber of E over the target point. The construction is the same as for topological or smooth bundles, but it respects the holomorphic structure if the map is holomorphic. But now, what can we do if we have a bundle over X and we want to construct something on Y? Again, let us have the same situation. Holomorphic map of complex manifolds. And now a bundle on X. Over X on X. Then consider the local sections. So for any open subset in X, we have the space of holomorphic sections. So if we want to construct somehow to construct a bundle over Y, we shall look at the sections. So we first try to define something on Y, which probably will play the role of sections of a new bundle. Let us define for any open set, say V, Y, consider or define gamma with subscript V to be by definition the space of sections of initial bundle over the pre-image of V, which is open in X. The obtained set of vector spaces or abelian groups may or may not correspond to sections of some vector bundles. Oh, correspond better to say. To the set of this type. For some holomorphic vector bundle F over Y. Well, first of all, how may it happen that it does not correspond? The simplest case is when the map from X to Y maps the whole of X to a single point in Y. Then most of these guys are zero. In any case, we see that, for example, if our map to Y goes through some point, small y in here, then if V does not contain that point, then gamma V is zero. If V does contain the point, then gamma V is, who can say what will it be? It will be, look at here. Then the preimage of such an open set is the whole of X. So what we get is the space of global sections of E over X. All right. So we see that the space gamma V depends on V in a very irregular way, I would say. So on the other hand, for if we would have a bundle for a vector bundle on Y, let me introduce the notation. Let me denote for an open set for V in Y, open. Let me denote O of V, the space of holomorphic functions on V. So I continue. On the other hand, for a vector bundle of rank k on Y, and for a sufficiently small open set, the space of the local sections of that bundle, okay, F. I do know this would be bundle F. Is nothing but the space of holomorphic functions taken k times, because the bundle has to be trivial on a sufficiently small subset, right? And this contradicts the property here. So in this example, we did not manage to construct a holomorphic bundle. In fact, if we used the notion of a sheaf, then for any map from X to Y, and for any bundle E, we would obtain something on Y, which we would call a sheaf. But since we are not interested in sheaves, we simply say that in some situation we can construct something good, and some situations we cannot. So what will be the moral? If the map F is such that the resulting space of a set of data gamma V if it results in such a set gamma V that for small subsets, open subsets, for small open V, gamma V is OV k times, where k doesn't depend, where k is always the same, is everywhere the same. Then we obtain rank k bundle, vector bundle, vector bundle F on Y such that gamma V equals gamma VF. Why it happens so? If you look at, if we have for two small subsets, V and V prime, check that on the intersection, the spaces gamma v, which is each of them is like set of vector valued functions. Oh, sorry. Not too bad. Wait. Not too bad. The space gamma v intersection v prime receives two bases. One from restriction map gamma v to gamma v prime, and from gamma v prime to here. And these two bases will be related by a holomorphic matrix valued function. And these will become the transition functions of a new bundle. So these are the way in such a situation we simply denote the results in vector bundle F as the direct image F lower star E, which is a vector bundle over Y. Okay. I hope to start the next lecture from an example which will clarify something, I guess. And it's enough for today. Thank you very much.
Thank you.
Any questions? You don't ask questions. This is very bad. Okay. See you in a week.